Okay, so welcome back to this advanced manufacturing process modeling course. So this lecture will be the last lecture of the course, and because already we have covered a vast syllabus, and considering that fact, the rest three modules of the course I have combined, and trying to will be presenting to you and discussing with you in a simpler manner, so that it becomes easier to grasp. Of course, it can be covered in more detail, in depth. We are basically planning to launch a new course in near future to discuss further details of these topics, and also analogous topics of interest, so that it can become more enlightening, and it can also serve the purpose of both the students who are going to become industry professionals, and as well as students who are going to become researchers or academicians in their career ahead, so that it can serve both their purposes. So with this, let us start with the final lecture today. So we will discuss the transport phenomena involved in case of metal or ceramic injection molding processes at the first. So please recall that we have discussed in detail about the transport phenomena that is involved in case of metal and ceramic injection molding process. So to give you a brief overview, so so in case of MIM, that is metal injection molding, or in case of CIM, that is ceramic injection molding. So basically we analyze the flow behavior of the feedstock. So feedstock is what? Feedstock is nothing but the slurry of the powder, that is, it can be metal, it can be ceramic, and the binder, that means the polymeric binder system. So which are basically responsible to provide the necessary flowability to the discrete powder particles, so that it can fill the complex contour die cavity of the targeted component that needs to be developed by MIM or CIM route. So when we use metal powder, we call the process as metal injection molding, and when we deal with ceramic powders, we call it as ceramic injection molding. But the fundamental interlying principles of their of the both the processes remains the same. So how do we investigate the transport phenomena involved in MIM and CIM process? So basically the physics is same like any other flow processes in like we discussed in case of casting, welding, additive manufacturing, and so on. So we need to solve the governing equations of mass, momentum, and energy. So we need to start with the continuity equation when there is no mass exchange. So the equation takes the following form, that is del rho del t plus grad rho v is equal to del rho del t plus grad del x rho u is equal to 0. So if the flow is steady, that means there is no change with time, then del rho del t, variation of density with respect to time, it becomes equal to 0, and when the flow is incompressible, then the there is density is uniform across all the region, and there is no change in density, the rho is constant. So then this equation gets reduces to this grad v is equal to del u del x is equal to 0. That means del u del x plus del u del y plus del u del z equal to 0. Okay. So so where v is the velocity vector, and u1 E plus E1 cap plus E2 U2 E2 cap plus U3 E3 cap, where E1 E2 and E3 are unit vectors along the 1 2 3 coordinate axis. So you can assume it as x y z, and the momentum transport equation. So here you can see that the momentum transport equation. So then in case of momentum transport equation, there are the following terms like inertia term, so which is rho del u del I del u del t plus u del u del x, which represents the rate of change of momentum due to the velocity field. So, and the viscous stress, that is the term del t del x, accounts for internal friction within the melt, and pressure gradient del p del x term accounts for forces due to pressure variations, and gravitational forces, that is rho g, represents the influence of gravity on the melt. Basically it is the mixture of polymer and powder flow. So yeah, as I told, rho is the density of the feedstock, I mean that is the mixture of powder and binder. Use the velocity component in the ith direction. Tau is the deviatoric portion of the stress tensor representing viscous stresses. P is the pressure field, g is the gravitational acceleration along the I axis. So gravitational acceleration vector g is equal to g1 e1 cap plus g2 e2 cap plus g3 e3 cap, which becomes equal to gi ei bar. So I mean so here this further like energy equations are not mentioned, because they are basically, it will become a mere repetition. Then the idea is to give you the idea about the what are the different conservation equations need to be solved to investigate the transport phenomena involved in case of MIM or CIM process. Okay. So I mean so heat transfer equation is basically, it takes the following form, that is rho Cp del t plus rho Cp v del t minus rho phi mass delta h, I mean grad Fs plus grad q minus I mean tau, I mean del v minus q dot is equal to 0. So here q dot is nothing but the heat generation term. Okay. So I mean so injection pressure overview. So pressure is required to overcome resistance to flow caused by feedstock viscosity, friction and mold geometry. Insufficient pressure may lead to defects like short sorts, while excessive pressure can damage the mold or cause flash formation. So key influences on injection pressure. So feedstock viscosity and temperature, mold geometry including cavity complexity and wall thickness, and frictional losses in runners and gates. So they are the key influencers of injection pressure. So the equation for pressure drop can be written like this. So delta P is equal to 12 eta LQ H by divided by H cube W. So this is an empirical equation of the, I mean pressure drop. I mean it can vary across I mean different conditions. For the present case it has been written like this. So here L is the flow length, Q is the volumetric flow rate, H is the cavity height, and W is the cavity width. So now if we focus our attention to this typical case study, where you can see that I mean the different defect formation generally happens if the die design is not proper, if the transport phenomena is not investigated to design the die. In case of, I mean so here the example is taken for a typical metal injection molding process of a steel powder. I mean so then this kind of defects forms. What are those defects? Like oiled lines, like I mean black lines, and I mean more I mean severe of them is the short sort, that means incomplete filling of the cavity, and also analogous experimental validations are shown to understand that how these defects can arise. So so I mean so you can see that, so these are basically the examples of short sort when there is a change in, I mean switchover volume is there. I mean when there is change in volume on the cross section of the flow path, and also the requisite I mean injection pressure is not provided, or the I mean velocity, I mean viscosity of the feedstock slurry becomes much higher, and the enough shear rate cannot be generated by the, I mean by the plunger, which is or the screw device that is present in the injection molding equipment. So that can cause, and also it can be responsible, it can happen due to premature solidification of the polymer molten polymer matrix that is responsible to ensure flowability of the, I mean metal powder particles. Okay. So defect visualization. So number one is weld line. So it's a weld line is basically used to predict the location of weld lines where two melt fronts meet, and then powder binder segregation is shown as a black line, where high shear rates in certain regions of the mold caused separation between the powder and the binder, leading to defects like black line. So, these are the example you see, this is the simulated and this is the experimental validation of the black line, that means which shows the so the sorry, this is basically the concept of weld line, where two fronts are meeting, and so this is the example of the this black line, where you can see the powder binder segregation predicted by the simulation, the transport phenomena, that is the CFD model presented by predicted by the CFD model is exactly matched with the experimental observation. So, these are basically so this case study shows the essence of developing process model in case of powder injection molding processes, which can effectively reduce the defect formation and can significantly improve the product quality, and also it can cause the improvement in the desired quality characteristic, achieving the desired quality characteristics in the developed parts. So, here it is the different process conditions has been first formulated based on design of experiment approach by Taguchi design of experiment approach, and then as per the different conditions, different process conditions, a number of simulations has been performed to identify the best set of parameters, and the outcome as obtained here, the filling time. So, the flow of the melt found to be uniform, and the melt front progression was consistent across all switchover volumes. And cooling time, optimum cooling time has been reduced from 12 second to 10 second without compromising part quality, and increased packing pressure from 30 to 40 MPa, improved dimensional stability and reduced warpage in green parts. So, you can see that, so based on the the process model, we could optimize the injection pressure, we could optimize the cooling time, we could optimize the filling time. So, all the so and then these optimum values can lead to the development of defect free parts. So, so this is basically the essence, is like any other process model we have discussed for other manufacturing processes. Here also the goal is twofold: number one, to gain insight into the physics of the process, and number two is to optimize the process conditions. So, going ahead, if we discuss the finite element based sintering model, you know that this sintering model can be effective to understand the sintering kinetics and to optimize the sintering densification by adjusting the temperature and time and also the heating rate. So, all those variables which impacts the microstructure and also the densification, shrinkage in case of sintering of the metal injection molded or ceramic injection molded green compact. So, here this is a typical constitutive model, a phenomenological constitutive model is shown for sintering densification, which is proposed by Kim et al. It is based on Newtonian viscous flow and thermoelasto viscoplastic model, where the material is considered to be isotropic in nature, and the total strain rate in this model consists of 4 terms which are related by this expression. So, total strain rate epsilon dot total is equal to epsilon dot E, that is the elastic strain rate, epsilon dot Th, that is the thermal strain rate, epsilon dot Vp, that is the viscoplastic strain rate, and epsilon dot S is the free sintering strain rate responsible to cause the densification during sintering. So, where elastic strain rate can be assumed to be linear and isotropic. So, thus it can be expressed as per the Hooke's law, sigma dot is equal to d epsilon d E epsilon dot strain rate into strain rate dot to the power E. Okay. So, how we are arriving to this expression, like as we know that from Hooke's law, that stress varies with the strain, proportional to the strain. So, then proportionality constant here is D. So, here we are, so then we can also write that del sigma by del T is equal to D, because it is a proportionality constant, del epsilon by del T. So, that is what is written over here. So, del dot is equal to D epsilon dot. So, this is what is shown over here. Okay. So, then the D is the elastic stiffness matrix for isotropic material. So, the thermal strain rate epsilon dot Th can be expressed as epsilon dot Th is equal to alpha T dot into I, where alpha is the thermal expansion coefficient, T dot is the temperature increment or decrement rate, and I double bar is the second order identity matrix. And the free sintering strain rate epsilon dot S for isotropic material is expressed as epsilon dot S is equal to minus 1 by 3 rho dot by rho to the power S and I. So, I is the identity matrix. So, where rho dot by rho to the power S is the free sintering densification rate, which is a phenomenological expression of relative density and temperature as derived by Kim et al. And co-workers. The free centering stress or equivalent Laplace pressure according to Olevsky's continuum model is sigma s is equal to P L is equal to 3 gamma by R 0 1 minus theta square, or sigma s is equal to P L is equal to 3 gamma by R 0 rho square. Okay. So, here so this is basically the porosity term, that is the theta, and 1 minus theta is the densification term. So, then so this is a brief overview of the continuum mechanics based phenomenological constitutive model of sintering, and that can be utilized for finite element modeling to for finite element modeling of the sintering densification phenomena, and the stresses and the densification shrinkage happens during sintering can be effectively predicted. Okay. So, and then the another concept is to molecular dynamic based simulation of sintering. So, in the previous slide, so that the you see the continuum model of sintering is valid for so investigating the part level features, densification, shrinkage, etc. But what happens at the length scale of individual powder particles? So, to understand that physics, we need to go to ab initio modeling technique such as molecular dynamics, because their continuum model is not valid. So, in the input for MD simulation is set by the following points, like selection of the potential, and then selection of the ensemble, selection of the integrator, selection of thermostat and barostat to set initial positions and velocities, and also selection of boundary condition, selection of time step and cutoff distance, etc. So, so the flow chart for basic steps of molecular dynamics simulation is setting initial position, velocity, followed by calculation of force using interatomic potential. So, and then solving Newton's equation of motion with the help of proper algorithm. So, what is basically the Newton's equation of motion? If I write here, so here it is m I d2 r I bar by dt square is equal to summation of f I j. Okay. So, where j not equal to I. So, here your m I and r I are the mass and position vector of the ith atom, and so and also the f I j is basically are the mutual interaction force of the between the ith and jth atoms. So, this is a typical, so P is equal to mf. So, this is basically the Newton's equation, which is the fundamental of any physical any process. So, then so this Newton's equation of motion has to be solved and with the choice of a proper algorithm, and then extraction of the required data. So, there are some fundamental models that are generally studied to get the insight into the sintering densification in the ab initio model, or two sphere model, or 3 sphere, 4 sphere, particle substrate model, particles of different size, sintering of between particle of different sizes and two different particles having out of two different materials and particles arranged in long chain. So, these are the following papers. If you are interested, you can go detail. Now, if we show a typical case study from our own work with alumina, I mean nanoparticles, nano powder. So, you can see I have already explained while discussing the powder metallurgy module about the coalescence between two different spheroidal powder particles, and then subsequent initiation of neck formation, and then neck growth, and then finally full coalescence of the I mean neighboring powder particles. So, here it is a typical molecular dynamics model has been developed. I mean where I mean the Newton's equation of motion has been solved, and then here basically the I mean Strage Mintmeier potential has been used with some modifications to simulate the I mean this sintering densification, and we could effectively predict the growth of the neck, neck growth temperature with respect to the heating rate, and we could also predict that both neck size and shrinkage ratio follows power law relation in time, that is x by a to the power n, which varies as t, delta L by L0 to the power m varies with t. So, where n and m are the exponents, x is the neck radius and a is the particle radius. So, the exponents are dependent on the mechanism of sintering. Okay. So, you see here also that with the increasing time the neck size also increases, and the neck size is higher in case of a lesser powder particle, and neck size reaches at a higher value at a lesser time. So, in case of smaller powder particles, like in case of 20 Armstrong powder particle, it is much faster. So, it signifies that with the decrease of the powder particle, so if with the decrease of the powder particle size, the sintering kinetics becomes faster. Okay. So, we have already discussed the reasons in detail when we have discussed the powder metallurgy module. However, how we can simulate. So, this is a brief case study overview, and if you are very interested, please go through to this paper to go learn about further details. Okay. And then so now we have discussed the brief overview of the process modeling aspects applied to MIM or CIM processes. Now, we will discuss the brief of process modeling aspects on applied to metal forming. So, before doing that, we will discuss about the forming limit diagram, because forming limit diagram serves as a key diagram to investigate the formability of the sheet metals, because sheet metals are the, like I told when I discussed about the forming module of the course also, that so in our daily life also we come across several parts which are developed by from sheet metals. So, sheet metal forming has a big role to play in our in the industrial parlance and also our day to day usage point of view. For example, the car bonnet is also a example of sheet metal forming, and also like another example I can give so like sheet metals are used for making several artifacts, and also you might have seen the complicated designs of several lamps and all that you generally see in airports. There are also a great application of sheet metal forming is there. So, here let us come back to the forming limit diagram. So, this is a typical forming limit diagram is shown where it is an essential tool in the field of sheet metal forming, providing valuable insight into the formability of the sheet metals. So, it helps in predicting and preventing defects such as necking and tearing during forming processes. So, what is FLD? So, FLD is a graphical representation that depicts the limit strains a sheet metal can withstand during forming without failure. So, you can see from these points that, so here two typical forming limit diagram is shown for titanium alloy sheet, this is at the top, and then it is for aluminum 6061 alloy. So, both of them are typically very much useful in terms of usage in sheet metal forming. So, you see that at the right side of the origin if the strain values minor strain values goes beyond a safe limit, it causes crack formation, and in the left side it goes beyond a certain value. I mean, it is, if it is lesser than certain value, then it causes wrinkle in the sheet metal. So, similarly it is true in case of I mean in case of your both aluminum alloy and also for the titanium alloy. So, so here this diagram shows the relationship between the major and minor strains at various points on the metal sheet just before the onset of necking or fracture. So, the FLD helps determine whether a given deformation path will lead to a successful part or result in failure. Okay. So, the major strain is the largest principal strain experienced by the material, and the minor strain is the smallest principal strain, which can be tensile or compressive or even 0. Okay. So, basically FLD depicts the zone, deformation zone, it decides the deformation zone for that particular material, where it can be processed without causing defect formation or failure of the sheet metal to part development. So, significance of FLD is failure prediction, process design, material selection and optimization. So, constructing the forming limit diagram, the construction of an FLD involves several steps, which can be summarized as the sheet metal testing as per Nakajima test and Marcy-Niak's test. So, these tests are named after their inventor scientists. And then number 2 is measuring strains. During the tests, strain gauges or digital image correlation techniques are generally used to measure the strain values at different points on the sheet, and then plotting the FLD. So, the major and minor strains are plotted over a graph, and x axis represents the minor strain and the y axis represents the major strain. So, understanding the forming limit curve. So, the FLC is the central feature of the forming limit diagram, and typically has the following characteristics: a positive minor strain, 0 minor strain, negative minor strain, as we have discussed in these two plots for both titanium and aluminum alloys. An interpretation of FLD, biaxial stretching, uniaxial tension and drawing. Okay. Application of FLD in tool design, process planning, quality control, and limitation. Of course, major limitation of FLD is the material dependency, because it is not generic across different material, and then strain path dependency and simplified geometry. And advances in FLD, digital image correlation, multi-dimensional FLDs and finite element simulation are the advancements can be done or directed towards further achieving further accuracy in FLD. So, here this is a typical example, again a case study for rolling simulation, finite element modeling of the rolling process. So, you can see so, this is here the material is basically a aluminum wrought aluminum alloy, that is 2000 series aluminum alloy and silicon carbide composite. So, okay, that means silicon carbide reinforced wrought aluminum alloy composite. So, what this finding signifies, the simulation basically helps in identifying that what is the optimum thickness reduction can be achieved in the rolling process without causing crack formation. So, a major damage that happens in case of rolling is basically edge cracking. So, as the reduction increases, edge crack initiates, propagates, and when with crack length increases from 19 to 28 mm, it becomes impractical to use the rolled part and it has to be rejected. So, the simulated edge damage morphology closely matches with the experimental results. So, again here it is shown as the essence of the process model. So, in the of course, in the solid mechanics domain, so there, because you can see this doing these experiments and by trial and error fashion to identify the optimum thickness reduction that can be achieved, and also the optimum rolling speed, it can become cumbersome and it can also be time and cost intensive, and moreover in the development of process model offers a opportunity to couple the macroscopic and microscopic phenomena, and also even the dislocation level plastic flow of matter, the science involved in it can be coupled with the conventional continuum model to understand deep into the mechanism responsible for plastic flow of matter. Here the example is shown in case of rolling, and also it is useful as a process control tool, because you can see from this results very well, you can understand that it basically predicts that up to a 20% thickness reduction at one go, at one pass, there is no edge crack formation happens, and so these findings have been validated with the experiment also. So the developed model can be effectively utilized for several other materials which are needed to be processed via rolling. So again, a separate case study for a different metal forming process, that is the case of wire drawing. So you can see, so these are basically the finite element model of the wire that is undergoing drawing, and also the die, and also this is the model of the drawn wire. So wire drawing, as we have discussed the case of extrusion and wire drawing earlier. So it is basically the drawing of the wire within a conical aperture or die. So here the difference with extrusion is there. Here there is a puller block which pulls the rod out or the wire out. So then in case of wire drawing, so here you see the typical finite element modeling that has been done with considering 8 element hexahedral element, and considering 8 nodes hexahedral elements so here you can see the typical results of stress and damage distribution. So you can see that the stress distribution, stress is higher in the surface of the wire which is undergoing drawing through the conical aperture or the die, whereas the damage is higher at the center. So this is the you can see the typical stress distribution curve, which shows higher stress at the periphery of the wire undergoing drawing, and also higher stress values near the die exit. Okay. And here this is a typical example where you can see the damage is higher at the center rather than at the surface. So you can very well predict the limit, like in case of the rolling we have discussed, one can predict the limit up to which the material can be strained, the strain value. So that also can be can give a proper idea about the reduction ratio that can be achieved in case of wire drawing, and how many passes are the material has to be subjected so that it can be uniformly deformed and without causing localized damage to the drawn wire, and thereby the process can be optimized. Okay. So, so these are some typical this animations shown for different metal forming processes. So this is a classic example of forging, and this is the example of rolling that we have discussed, and again you see the example of wire drawing, and also you can see the example of shearing. Okay. So, yeah, so this is how the process modeling can give you the feel of the process. It can give you the mechanics involved in the process, and also it can provide the best set of parameters. So these are basically all physics informed models that can serve both the purpose of knowledge generation and also the process control. So with this we are done with the brief overview of the metal forming and process modeling aspects. Now we will discuss briefly about the machining and process modeling aspects. So so machining is basically it is a critical process, because 80% of machine tools used in manufacturing are related to metal cutting, and it also leads to around 10 to 15% of metal produced is converted into chips during machining. So this is a typical machining setup, you can see. So this is a typical cutting tool. This is a typical example schematic, shows the example of turning, where you see the rake angle. The rake angle is basically the rake face, the cutting face, and the perpendicular to the direction of the I mean direction of cutting, that is the tool is direction of tool progress, or the direction of cutting perpendicular to that, and the between the rake face of the tool the angle forms is called basically the rake angle, and then the angle between the trailing surface of the tool and the machined surface of the workpiece is called the clearance angle, and here V is the cutting velocity. Okay. So, of course, you can understand that the tool, the machine tool, the cutting tool that has to be utilized for machining has to have higher hardness than the material which is undergoing machining. Okay. So, the impact of rake angle is higher rake angles reduce cutting forces, but also weaken the tool tip and decreases heat dissipation. So, maximum rake angle for high speed steel cutting mild steel is 15 degree. So, this is a typical example. So, you can understand that you cannot just increase the rake angle without considering about the fact of the the strengthening of the tool tip, because otherwise it can cause tip fracture. So, which is not recommended. So, there is a limit of the rake angle that can be considered, and which varies material to material. Like in special cases 0 or negative rake angles are used for brittle materials, that is carbides or diamonds, to strengthen the tool tip. Okay, because brittle materials are also showing very high hardness, and it can very well cause it is very difficult to machine them, and also if the cutting tool tip is not strengthened by negative or 0 rake angle, then it can very well fracture the tool tip. So, hence negative rake angles are used. Okay. So, but for ductile metals mostly the positive rake angles are used. Okay. So, chip formation. So, chip formation is a fundamental process in machining involving material removal due to plastic deformation and shearing. So, this is basically the example of the primary shear zone that forms between the uncut. So, I will say this is the uncut region of the workpiece, okay, which is undergoing machining and getting removed in the form of chip formation. So, the primary shear zone forms between the uncut region of the workpiece and the chip that is getting generated, okay, and the secondary shear zone forms between the chip and the tool which is responsible for machining. Again the example is given in case of turning. Okay. So, so the chip formation is a fundamental process in machining involving material removal due to plastic deformation and shearing. So, the process, the metal in front of tool's rake face is first compressed elastically and then plastically in the shear zone, and separation occurs as yielding or fracture, creating a chip that flows over the tool rake face. So, types of chips: discontinuous chips and continuous chips. So, discontinuous chips are intrinsic to the machining of brittle materials. So, the material fractures periodically, forming segments easier to handle, but leads to a rough surface, whereas continuous chip is intrinsic to the ductile materials, and you see but in this case the chip formation causes if I draw a typical example. So, you can see this is your cutting tool and this is the uncut region and this is the workpiece, and then the chip generated can get coiled up. So, that is also another trouble, it can cause trouble. So, that is why in case of machining of ductile materials where continuous chips are generated, chip breakers are essential tools that has to be present. Okay. So, shear zone in metal cutting. So, as I already told and shown, so this is the primary shear zone and this is basically the secondary shear zone. Okay. So, these two shear zones are generally forms in case of metal cutting. So, also leading to chip formation. So, two models are used to describe the shear zone. Number one is thin shear plane model. So, it assumes the deformation occurs along a very thin planar surface, convenient for analysis, but physically impractical because velocity transitions from cutting speed to chip speed would require infinite acceleration, which is not practical anyway. And the other one, that is thick shear zone model, it is more practical and realistic because it allows for I mean finite time for transition in velocity and shear stresses, making it a more practical representation. So, key parameters, number 1 is shear angle. So, the angle between the shear plane and the cutting speed vector is called the shear angle. Okay. And so, now coming to the major classification of machining process applied in the turning process is orthogonal cutting and oblique cutting. So, what is orthogonal cutting? Orthogonal cutting is the case where the cutting tool remains, I mean, perpendicular to the direction of the, I mean, cutting direction of cutting. So, it is basically a, I mean, very few occasions we can see this kind of I mean orthogonal cutting, but it can be observed say in case of parting off of a I mean of a say shaft, okay, or it can also happen, I mean it can be observed in case of tube turning, but otherwise most of the I mean machining turning involves oblique cutting. However, orthogonal cutting is simpler in terms of analyzing the I mean complex stress state and to I mean define the cutting forces, that is 3 dimensional in nature. So, that is why I mean we generally go for I mean orthogonal cutting we take as an example to hypothesize the mechanics involved in machining. So, the in case of orthogonal cutting, the cutting edge of the tool is perpendicular to the cutting direction. The cutting process involves only 2 dimensions, the cutting speed and the feed rate. So, these are I mean this is so cutting speed and feed rate serves as the governing I mean parameter in case of I mean orthogonal machining or orthogonal cutting. Okay. So, and then the oblique cutting. So, the case of oblique cutting is I mean, so the cutting edge of the tool is inclined to I mean inclined to at an angle to the cutting direction, resulting in 3 dimensional forces. So, I mean the more representative of real world machining processes like turning and milling. Key takeaway I mean in case of, so for simplicity we consider the case of orthogonal cutting to hypothesize the machining processes where we can I mean consider about the I mean only 2 dimensions, that is cutting speed and feed rate, whereas it becomes I mean 3 dimensional forces in case of oblique cutting, which is a more genuine representative of the machining process involved in case of turning and milling. Okay. So, this is so this slide shows a typical example of the I mean machining process. You can see that how it, so this is you can see from the I mean simulation itself that it is a case of machining of a typical ductile material, because you can see the example of continuous chip formation. So, here you need chip breakers, okay. Otherwise, what can possibly happen? So, these continuous chips can also modify the cutting edge of the tool and can result in BUE, that is built up edge formation, which can also I mean can generate a blunt cutting blunt tip of the cutting tool, and that in return can also degrade the dimensional tolerance of the machine surface. So, yeah, so then you have to have chip breakers in place. Okay. So, this is a typical example of finite element based process model that is can be utilized effectively for simulating the the machining process. Okay. So, here you can see the contours of plastic strain of chip formation process. I mean the stress state experienced not only by the workpiece, also the I mean strains that is I mean experienced by the I mean chip, which is generating I mean from the this machining process. Okay. So, here this is a I mean so then so the contours of plastic strain of chip formation process of cutting trial 1 giving 20 C initial workpiece temperature. So, this is an example of smooth particle hydrodynamics or FE modeling of cutting force and chip formation during thermally assisted machining of Ti 6 Al4B alloy. Okay. So, with this we have discussed about the brief of the I mean I mean brief of the machining aspects, and also how the process modeling, I mean of course finite element based process models can be applied to understand, grab insight and to optimize the process variables involved in machining processes. So, as I told in the beginning that I mean we can we are, I mean we are in the process of formulating and proposing a new course which can dig deeper into these aspects and also other analogous aspects. So, hope you have enjoyed the course and grab insights into the I mean several topics that I have discussed over several months, and I will be happy to interact, and any students attending this course can write to me. If they are interested to do research with me, even they are I mean welcome to write to me, and any doubt if you have, we can try to clear the live session which is organized on I mean 28th March. Thank you.